Step outside on a brisk winter night and catch a single snowflake on your glove. Hold it close to your gaze. 6 arms spread with fractal precision, each branch echoing the next in icy miniature. Rotate the flake 10 degrees, 20, 30. Every turn returns the same silent geometry, as if nature had traced one crystalline stanza and set it spinning through space. We find such balance enchanting because it whispers of order, a suggestion that the universe is composed not merely of things but of rules. Deep, hidden symmetries that choreograph matter and light. In the language of physics, symmetry is far more than decoration. It is a promise. When the laws of nature look identical tomorrow as they did an instant ago, a quiet covenant forms. Energy must be conserved. Slide a laboratory bench a meter to the left and discover the equations stay unchanged. Momentum is guaranteed. Tilt your head beneath the stars, pivot through the darkness, and because the cosmos presents the same face in every direction, angular momentum endures. These invisible guide rails trace back to one mathematician, Emmy Noether, who revealed that every conservation law is the echo of a symmetry in disguise. Yet perfection alone cannot write a story. Imagine a universe with flawless symmetry, no wrinkles of imbalance, no tiny deviations. Stars would not ignite. Fusion requires a loophole in perfect mirror law to let protons slip past their mutual repulsion. Galaxies would never coagulate. Gravity needs initial asymmetric seeds to gather dust into spirals of starlight. Even life, mirrored hands constructing mirrored cells, relies on a cosmic preference. Amino acid spirals, all curl left. Sugars spiral right. Somewhere in the earliest moments after the Big Bang, symmetry cracked just enough to widen possibility without erasing harmony. Across the heavens, these fractures shine. The sun above us balances on a razor's edge of time symmetry. It's converting 4 million tons of mass into light every second, yet never flickering beyond a whisper. Deep within its core, the weak force betrays mirror symmetry, allowing rare interactions that set the stellar furnace to a simmer instead of an explosion. Farther still, in particle colliders beneath the Alps, physicists hunt for vanishing differences. Subtle violations of charge and parity that might explain why we have galaxies instead of a sterile sea of light. Tonight, let us follow the compass of symmetry from the elegance of Noether's theorem through the cosmic kill of starlight. Onward to the purposeful fractures that give the world texture and us a place within it. We will see how symmetry shields energy, how breaking it gifts mass, how the slightest tilt of a universal mirror chose matter over antimatter, paving the way for galaxies, worlds, and wondering minds. In the balance between order and imperfection lies everything we cherish: the steady glow of morning, the crystalline dance of snow, the heartbeat syncing with the hush of night. Welcome to Symmetry, the code that makes stars burn. Berlin, winter of 1917. Albert Einstein, pockets full of pipe ash and head full of curved space-time, paced the parquet floors of his apartment. He had bent gravity into geometry. Planets orbited because valleys in space guided them, but a quiet arithmetic haunted him. In Newton's universe, energy moved from one ledger to another with immaculate clarity. In Einstein's, the books came up fuzzy. Shift your coordinates. The energy stored in a gravitational field seemed to leak away or reappear like a conjurer's coin. Down the rail line in Göttingen, mathematician David Hilbert sensed the same discomfort. He could wrangle tensors as deftly as any physicist, yet the balance sheet refused closure. So he turned to a colleague who, until then, lectured in borrowed classrooms because women were barred from professorships. Emmy Noether. Where others saw equations, Noether saw underlying harmonies, structural chords that persisted when variables flexed. Hilbert presented the energy riddle. She retreated behind chalk-dusted doors. Months later, she resurfaced with an answer so distilled it felt inevitable. If a physical system's equations remain unchanged, invariant, under a continuous transformation, then some measurable quantity must stay constant. Noether had not merely patched Einstein's bookkeeping. She had revealed the very mint that prints nature's conserved coins. The geometry of gravity, the glide of an electron, the spin of a galaxy, all would now be judged by their hidden symmetries. Translate a pendulum experiment forward 1 millisecond. The laws guiding its swing do not blink. That almost trivial statement that physics is indifferent to the tick of the clock locks in the conservation of energy. Slide the entire laboratory a meter east. With no preferred origin, momentum must balance eternally. Rotate the apparatus under the ceiling lamp. Because the equations care nothing for orientation, angular momentum spins on inviolate. This is Noether's theorem in its purest breath. Symmetry births conservation. The proof runs through the Lagrangian formalism, but its soul is simpler. Continuous symmetries, meaning smooth changes you can dial from zero to a whisper. Forge currents, quantities that neither appear from nowhere nor vanish into the void. An unchanging timeline yields an energy current. A featureless landscape yields momentum. A directionless cosmos yields angular momentum. Every polished gem of invariance casts a shadow that we measure in laboratories and feel in our bones. Even abstract forces obey. The electroweak field stays invariant when its quantum phase rotates. So, electric charge cannot be created or destroyed. Quantum chromodynamics respects color Su-3 symmetry, binding quarks under an unbreakable book balance of color charge. With a single stroke of chalk, Noether transformed bookkeeping from empirical habit into mathematical destiny. In the chapters that follow, these invisible currencies will pay the bills of the cosmos powering fusion in the sun, deciding why matter outweighs antimatter, and reminding us that every flicker of starlight is the dividend of a symmetry honored since the first moment time had meaning. Look up at midday. The sun pulses 150 million kilometers away, yet its brilliance scarcely wavers, never flaring hard enough to scorch oceans, never dimming enough to freeze continents. A constancy is no happy accident. It is the direct consequence of Noether's most familiar symmetry, the sameness of time. In the furnace at the sun's core, 4 protons combine to form a helium nucleus. To positrons, to neutrinos, and pure radiance. Because the equations governing that reaction remain identical from one heartbeat of the universe to the next. The bookkeeping of energy must balance with diamond precision. Every photon streaming through your window is paired with a fractional loss of mass inside the star. An exchange so precise that after 5 billion years, the sun's brightness has crept upward by only a third. Translation symmetry joins the vigil. Deep inside, pressure battles gravity, layer on layer. If space favored one location over another, momentum could bleed sideways, collapsing equilibrium. But momentum is conserved because space itself refuses bias. Therefore, the outward push of photon pressure matches the inward pull of weight everywhere, from equator to pole. Even tiny acoustic oscillations, helioseismic waves, reveal a star balanced by invisible Noether currents. Their rhythms confirming the sun's structure 2 parts per million. Symmetry does not merely describe the star, it keeps the light on, frame by frame, day after irreplaceable day. With Noether's ledger in hand, scientists learned to hunt the unseen. In 1919, during a total eclipse on the coast of Principe, Arthur Eddington measured starlight deflected by the sun. Energy momentum conservation carried along null geodesics of curved space-time. Predicted exactly the bending Einstein had dared to publish. The match crowned relativity, but the method was Noetherian. Trust the conserved current and test the geometry around it. Decades later, nuclear reactors puzzled researchers with missing beta decay energy. To preserve energy conservation, Wolfgang Pauli proposed an invisible lepton, the neutrino. 26 years on, Clyde Cowan and Frederick Rains caught neutrinos in a tank of water and cadmium chloride, vindicating Pauli and Noether at once. Particle colliders repeat the ritual daily. When quarks collide inside the Large Hadron Collider, detectors reconstruct spray patterns. Any imbalance in momentum or charge triggers alarms, either a detector glitch or a portal to new physics. Dark photons, supersymmetric partners, perhaps hints of hidden symmetries, still uncharted. Even the discovery of the Higgs boson hinged on closing an energy gap in decay products, assuring Noether's book's balance to the last electron volt. Across astrophysics, nuclear physics, and quantum field theory, conservation laws act like forensic lamps, illuminating invisible actors, exposing theoretical forgeries, and guiding explorers toward deeper layers of symmetry yet to be revealed. Physicists are magpies for elegance. Dirac once said an equation's beauty could outrank experimental proof, and history often rewarded that faith. Maxwell's perfectly symmetrical scroll fused electricity with magnetism. Einstein's field equations, spare as calligraphy, predicted black holes in an expanding cosmos. Time and again, symmetry has lit the path before evidence arrived. But a good compass can still mislead. For 40 years, theorists pursued supersymmetry, the notion that every fermion partners with a mirrored boson, racing quantum infinities in a mathematically pristine dance. Collider after collider probed deeper, yet no superpartners appeared. The universe, it seems, is willing to bend aesthetic rules if another subtler symmetry, or an exquisite asymmetry, better serves its story. The lesson is humbling. Symmetry is guidance, not gospel. It tells us where to look, which quantities to count, how to guess the next verse in nature's poem, but it does not guarantee the rhyme. When data disagree, elegance must yield. History's most creative moments emerge where perfect balance cracks. The lopsided decay of kaons, the tiny mass differences that let neutrinos oscillate, the electroweak symmetry broken by the Higgs field so particles could gain heft. Beauty still matters. It whispers the language of the deep. But it is the dialogue between symmetry and its fractures that writes the cosmos we inhabit. Gaze again at the midday star. Its brilliance is a paradox of precision and imperfection. Time symmetry keeps the energy books balanced, yet something else, a deliberate crack in mirror law, must tip the odds so protons confuse in spite of their mutual repulsion. Without that loophole, the sun would hoard its hydrogen in frigid silence. Too large a loophole, and it would erupt in a fatal flash. In Part 2, Symmetry ignites the sun. We will plunge into that nuclear courtroom. We will watch quantum tunneling sneak past perfect electrostatic symmetry and see the feeble, left-handed nature of the weak force slow the fusion rate to a life-friendly simmer. From there, we will trace how symmetry and its nuanced violations shaped every photon warming your skin. Every aurora that dances at Earth's poles, every heartbeat timed by the rise of dawn. The journey ahead is not merely stellar, it is personal. The warmth that ripens fruit and steadies climates is the direct consequence of nature's willingness to keep her deepest symmetries, yet bend them just enough to let stars breathe. Let us step into the furnace and witness that delicate compromise in action.